it just felt like.
Okay, so now we're in business. Now I think you can hear me. All right, so we're ready. Okay, so see if you can continue the streak here. How do I rewrite that differential form?
Well, the differential form dy equals f of x times dx.
Okay, so what would it be for this?
So,
There you go. I heard it. Say it again. Okay. So we write that in differential form. And now step 2. How do we undo a derivative? Integral or antiderivative? Yeah, okay, so we're going to do this to both sides.
Lowercase d. Is it an s?
Yeah, that's an S.
Okay, so what do I get on the left side then if I take the antiderivative of a derivative? They cancel, right?
Yeah.
Okay, and so my answer looks like sine x, but what do I have to include if I'm doing an antiderivative? Right, it's giving me back a general solution, a family of curves, plus c every time.
Oh, yeah, yeah, I thought it was something more complicated
No,
than that. Okay.
nothing more complicated.
Oh.
And so that, I'll flip that around so it's more conveniently written, but this is my antiderivative rule. The antiderivative of cosine x dx equals sine x plus c. Okay. Yes, sir?
So d of something is the same thing as d over dx.
That's the integral side.
No, it's not exactly, it's written, there's 2 ways you can look at this. It's just algebraically, all we've done is multiply both sides by dx so that we can use this form of the derivative in 2 ways. Either we could use it for doing the stuff that we just recently did with the linearization stuff, or we can undo the derivative with an antiderivative. There's kind of a way you can visualize it. When you write a derivative like this, you're thinking of it in terms of a slope. Okay, so you're saying that the change in this function with respect to x, and this is how we've always looked at it, right, as a slope of a tangent line. If you look at it like this, you're saying incrementally small pieces of this function behave like what? Like that. See, so but honestly, I think the easiest working way to think of it is just algebraically. Differential form just means that you're going to not write the derivative with respect to something, you're just going to multiply both sides by that dx. And it literally is just an intermediate step for us here to get to the antiderivative. How could we have done that a little quicker though? Well, I mean, now that you know the pattern, you probably just realize that, the antiderivative of that has to equal, right? The antiderivative of this has to equal that plus a constant, right? And so that's the way it's going to be for all of the derivative rules that we have, okay? What about, okay, there's one other one I think we ought to take a quick look at.
So
And
this is fairly easy, but it's
Yeah, it is.
too much thinking.
It is, yeah, it is. So you tell me then, what would be the antiderivative rule? And I'll print the sheet out and give it to you. I mean, you'll have to, I would just memorize it. I mean, it's one of those things that's, it's good to know. You have to do a lot of memorization in math, but knowing the derivative and the antiderivative rules is one of them. And you just gotta have a working knowledge of those. What would this one be? Let's take a derivative rule. If we start with the derivative with respect to x of, let's say, secant x. What is that? Yeah, actually, I'm gonna make it a little harder. Let's do cosecant, so we get a negative sign in there. Okay, what's that gonna be? Good. Negative cosecant x cotangent x, right? Okay, and there's a temptation to put the plus c on there, but that's only for the antiderivatives, right? Okay, so then what is the antiderivative rule going to be?
Equals the S,
So the integral or antiderivative of this, right?
equals, put a C in there, plus C.
Right, because we have to put the dx in there. Remember, that's, from the other day, that's how we always have to write an integral. There's three parts to it. There's the integral sign, there's the integrand, which is the function in the middle, and then there's the variable of integration, right? And it always has to be written in that format. The integral of tan dx or dt or whatever the function, whatever the variable is, the independent variable is, right, that we're anti-differentiating with respect to. So then what's the answer going to be? Cosecant x plus, I'm going to call it, well actually, yeah, I'll just call it C1. Okay. Well, you'll see why in a second here. What about that negative sign? That's a little bit inconvenient. We don't really want that negative sign there in our antiderivative rule, do we? Yeah, now, here's, and I could derive all these, but some of them I'm just going to give you. I mean, we could go through and prove each of these, but, in the interest of time, I'm not going to do that. Remember how with derivatives, it was really convenient for us to be able to do a few things. For example, we could always take any constant if we were taking a derivative. Say we were doing the derivative with respect to x of 13/7 sine x. And what could we always do with that constant? Yeah, we can always take any constant and move it outside of the derivative, can't we? Right? Okay, that is also true for the inverse process. We can do that for antidifferentiation also. So when we're doing an antiderivative, I can take this negative sign, that -1, just move it outside. Okay? It's just a constant that's being multiplied by this. The reason we can do that, rather than prove it algebraically, I will leave that for us to consider sort of theoretically or conceptually when we get to the next step in integration. You'll see why. You'll see why. Eventually we're going to look at this weird connection between antiderivatives and areas under curves, and then it'll be pretty clear why we can do that. So that's going to be in a couple of weeks, but we'll come back to it later. So then if I do that, if I pull that negative sign out front, yeah, good. So then if we do that, if we pull this guy out front, it's just a constant that's being multiplied by this whole entity. And so I've got an equation, right? What can I do to both sides of an equation if I have a -1 out here I don't want? Yeah, multiply or divide both sides by -1, right? And that just moves it over here. I'd have to distribute it, though, to this part right here. So -C1, we'll just call C. How's that sound? They're just constants anyway, right? We don't know what they are. And so that's our antiderivative rule, right? So in the case that you have a negative sign, what happened here? We can kind of generalize this too. In the case that you have, a negative sign in your derivative rule, it's just going to appear in the antiderivative rule also. Yes?
Would you take the minus C rather than plus C?
Well, yeah, you would, but what is C?
Yeah.
C could be any positive or negative constant. See what I'm saying? And so being as it's just this big umbrella that includes every conceivable real number, it doesn't matter that we put a sign on it, right? It could be positive or negative implied, it could be either one anyway, right? Okay, so one more, and we'll move on. Because this is the one that we're already using, and I just want you, this is kind of a cool, I mean, there's something you can kind of see, a pattern you can see that you'll come back to in math later. What if we want to do the same thing for the power rule, one that we use most frequently? So we've got the derivative with respect to x of, I won't even put the constant in there. We know how to deal with the constant. So we'll just do x to the n. What is that?
NX to the N minus one.
Okay, good, it's n. And I'm gonna, for reasons that will be a little mysterious to you right now, at the end, I'll ask you why I did this and you'll tell me. I'm gonna make that a k instead of an n. So what would it be in terms of a k? Okay, it'd be k x to the k minus 1. Good. So if I flip that around then, what antiderivative does that give me if I just flip it straight around? The antiderivative of what equals what? K x to the k minus 1 equals x to the k plus c1.
That C1's confusing.
Well, I'm just saying it might be different than our final c. I wouldn't have to do that. I could just call it c and then add stuff to it and just keep it going c. But I'm just saying it's going to be slightly different constant.
Okay.
Yeah, but it doesn't matter, it's just constant. Okay, so what can we do algebraically here? We could, you tell me. That doesn't look very good, does it? We don't want to have that, we really don't want to have the rule with some arbitrary constant involved in the rule. We really want to get to, right, is something just like this, where we can say the antiderivative of x to the n dx equals an answer, right? We want to have a power rule, a suitable power rule for antiderivatives. So we really don't want that k in there, that's just a constant. We don't want that in the rule side, we want that in the answer side. We want that to be part of the answer that this general rule is spitting out for us, right? Okay, so I could move the k out front. And then divide both sides by k, right? So those go away. And I end up with, if I do that, over here I'm just left with the antiderivative of x to the k minus 1 dx equals, how am I going to do this? Well, I guess we could write it as x to the k over k plus c1 over k, we'll just call c2, just some constant, some slightly different constant that we still don't know, right? Make sense? Is everybody okay with that idea, that the trick I'm playing with the constants there?
You're just.
Yeah, I mean, it's just remember, we still don't know what it is, we just have to account for the possibility that it's there. So if we want to find a particular solution, we can apply an initial condition and solve for that, right? Okay. Okay, but that still looks a little bit hokey, doesn't it? It doesn't quite look like what we want it to look like. We don't want to have, that's a weird rule to have the antiderivative of x to the k minus 1. I mean, think about how you're going to use this thing. You're going to use this thing when you're trying to do like an antiderivative of x to the 7th or something, right? And so we don't want that k minus 1. That's weird. We want that to be just a parameter, right? So how can we get from there to there? Think. How can we do that? This is actually, it doesn't seem like much, but this is good buildup for stuff we're going to do for the rest of the year in here. Is there a math trick we could apply? Say it again. Well, it's okay, that's what we're coming up with. And this is nothing fancy. This isn't anything calculus related per se.
Could you just add 1 to the k minus 1 and then add 1 to the x to the k?
Okay, kind of. Why don't we just say, let's just make a change of variables, or in this case,
Set k minus 1 equal n.
exactly, set k minus 1 equal n.
K, and then substitute the rest of the k.
That's it, right? all we really wanna do is transition from Ks to Ns, right? Where the K minus one that appears here equals the N that we want in our final answer, right? Does that make sense? So we're just gonna set up that equation, we'll make that transition. Here's our change of variables. N equals K minus one, right? And so this becomes that, right? What is our answer gonna look like? Well, if N equals K minus one, I have to be able to substitute in here, I've gotta be able to plug in Ks for my Ns, or Ns for my Ks, right? So what would K equal in terms of Ns? N plus one. Right? So all of these over here are gonna become N plus ones. Right? And then my answer just looks like, it's gonna look like x to the N plus one over N plus one plus, finally we'll just call that C now that we're done making changes to it. I guess we were done there, weren't we? And so there is my working power rule for antiderivatives.
How is K N plus one? How does that work?
Well, because we just said this is an inconvenient way for us to write this rule. So let's just make a little substitution. Let's just define some different variable N, which is equal to K minus one.
Oh, okay.
Okay.
Gotcha.
And we'll use that one
N
instead.
plus one to both sides, and it's basically.
Yeah.
Okay, gotcha.
Okay. And so here's our rule. And this is what you guys were doing with your calculus Jeopardy the other day, isn't it? You were able to tell me, when I gave you problems like this, the antiderivative of x cubed dx, you all told me the answer by just kind of, because you're smart, you just thought backwards. But now we can just use this rule, can't we, right? What would n be? 3, so my answer's gotta be x to the 3 plus 1 over 3 plus 1 plus c. Right? Okay. Make sense? Okay. So I'm not gonna go write down all the rules. They're there for you. You know them anyway. They're just the reverse of the antiderivative rules, or of the derivative rules. Let's just practice using these a little bit. Mainly, we're just gonna use the power rule, but I wanna talk about some techniques for doing antiderivatives, because there is sort of, these are a little bit tougher to do. Derivatives, and earlier in the year you would have thrown some at me if I'd said this, but now I think you all agree, derivatives really aren't very hard. You just follow the rules. You just have to be able to look at it and say, okay, what rule applies? Is it the product rule? Is it the quotient rule? And then just do the rules. Boosted or sort of powered up by the chain rule, right? The chain rule allows us to do layers, compositions of functions, but still you just follow the rules. Antiderivatives are not quite that simple. Antiderivatives, you have to kind of massage the integrand to make it look like one of the standard forms, or you can't do the integrand. You have to sort of do a lot of the work before you actually do the integral. With derivatives, you start with something and you do all the work in the process of taking the derivative. With an antiderivative, the work is just getting this in a form where it fits an antiderivative. Okay? So what about this one? This one, as it stands, the integrand, what is the integrand here?
X squared plus 1x over x squared?
Yeah, it's all this stuff. Right here is the integrand. Okay, we don't have some rule for that bizarre configuration of powers of x that we can turn to and say, okay, well, what is the derivative of what is that? That's not in the playbook, right? So what we have to do is we have to do some algebraic manipulation of that integrand to change it into a form or forms that we recognize. Any ideas what we might do? Does that make sense what I'm saying? This one is not one that, we don't have a derivative rule that ends up with this for an answer, do we? Right? So we can't play calculus Jeopardy with this whole thing. It's just bizarre. It's weird, it's random. It's not one that we'll use very often, probably just this one time.
Could you take it and put the x squared on top?
Okay, yeah. Well, how about, you mean turn it into two different
Yeah.
terms? Yeah, so what if we divide each term by x squared? So this looks like the antiderivative of 1 plus x to the, because I get x squared over x squared,
-2.
-2. Okay, fortunately, and this might make sense, because we were able to differentiate term by term, we ought to be able to, when we reverse the process, also work term by term, right? Does that connection, I mean, is that good enough rather than doing a formal proof? That has to follow, doesn't it? Because if we can do stuff like this, if I can take, for example, the derivative with respect to x of x squared plus sine x, and get what for my answer?
Plus cosine.
Okay, I ought to be able to anti-differentiate each of these terms separately and map them back to those starting terms, right? There's like a, call that a red arrow that goes there, and a green arrow that goes there. It's a two-way arrow. This direction means differentiation, this direction means anti-differentiation, right? But because the red arrow always goes to the red terms and the green arrow always goes to the red terms, I ought to be able to do my same trick up here, shouldn't I? Right? I should be able to break this up into two separate smaller antiderivatives, right? Which we can do. Now, whether we do this on paper or just in our head, I would say just in your head, there's sort of this intermediate step here where we can say, okay, that's the antiderivative of 1 dx plus the antiderivative of x to the minus 2 dx. And what are those equal to? What's this one? Yeah, x, isn't it? Right? Does that make sense? The derivative of what is 1? Well, you can even use the power rule if you want to. It's overkill, but you could, right? If we let x equal 0, isn't that what it would be if I had just the derivative of, antiderivative of dx? X to the 0 is just 1, right? What do I get over here? X to the 0 plus 1 over 0 plus 1, just x, right? That's one we usually just remember as its own rule, though. The antiderivative of dx is just x plus c, right? So we get back from this term, we get x plus c1, let's say, right? From this term, what are we going to get? What's our power rule tell us for that one? The antiderivative of x to the minus 2 is,
Negative. No, just kidding.
technically it would be x to the n plus 1, right? So what's that? -1 divided by -1 plus, call it C2, right? Okay, but we could maybe make that even a little simpler. Do we need both of those constants? No, you don't need to do that, right? We know that eventually, if I just have two unknown constants, the sum of those is just some other unknown constant. So you always just group, you don't need to write both of those. You always just lump everything into one big constant at the end, right? So we can just, for one thing, we can just do, yeah. What about this term? What's that gonna look like? Yeah, so right, so our answer just looks like x divided by -1 is the same as multiplying by -1. So I just get that. Right? X to the -1 just moves it to the bottom. Okay, make sense? So by splitting up that integrand, it ended up being very simple. Okay. Now later on in the course, and beyond that, next year, and the year after, and the year after, you'll look at some examples of, there are other techniques for dealing with how to change an integrand in really tricky ways, you know, that you can't just, where you can't do something algebraic that gets the job done. There's some other integration by parts and use substitutions and trig substitutions and all kinds of interesting techniques people come up with for doing harder integrals. But for now, we're just, everything we're gonna look at, we can do by just algebraically just tweaking things a little bit, okay? How about this one? probably doesn't jump out at you right now, but soon it will. That is another example of one that is clearly not gonna be one of our standard forms. We're only gonna have like, 10 or 12 of these antiderivatives that they all have to end up looking like for us to get answers, right? And that's certainly not one of them. That's a bizarre one. Right? If you look at this integram, I'm gonna have to do something to that to make it fit some patterns that we know.
You gotta break it up, right?
Yeah, how would I do that?
Integral, parentheses 2t squared, parentheses squared. With the dt.
Well, we'd use, not necessarily the chain rule. Yeah, we don't have a chain rule for antiderivatives yet. And we don't ever really get the chain rule per se, but we get something similar to that. But algebraically, what could we do to this? Because I have a polynomial to a power, right?
Go ahead and expand.
I gotta expand it out, don't I? Right, I've just gotta expand this thing out. So I end up with the antiderivative of a bunch of stuff. If I expand that out, what do I get? Good, I get first term squared, so 4t to the fourth, 2ab, right? So that's a and that's b, so minus 4t squared plus b squared, right? You know what I'm saying when I do that. We're just saying a plus b squared equals a squared plus 2ab plus b squared, right?
Yeah.
And now it's easy, isn't it? Now it's just we can break it up into 3 simple power rule problems. So we're done, right? And maybe we don't need, we can do those. You wanna do those, or should we just
Let's just do it.
do them? Okay, that's fine. So then what's this one gonna give us? So we get the 4 t to the fifth over 5, right? Minus 4 t cubed over 3 plus t. We done? Plus c. All right, now we're done. Right? Okay, that one, we've essentially already done that one. Skip that one. What about this one? Okay, that's not one that we know, is it? I mean, it's not one that, once again, now we have to do something to that integram. Now think in terms of the trig functions that we know. And it looks like this involves sines and cosines, right? So let's just write out the derivative rules we know for the like for the sine and cosine and tangent and secant ones, how about, right? So which of these might be helpful here? We've got antiderivative of sine x dx equals what? Negative cosine x plus c. We've got antiderivative of cosine x dx equals sine x plus c. We've got antiderivative of, now, we don't have a lot of these that end in tangent and secant, right? But we could differentiate, for example, tangent. The derivative of tangent is what? Okay, so we could undo that by saying the antiderivative of secant squared x dx equals tangent x, right? Plus c. And we know the antiderivative of secant is what? Okay, so if we write the backwards version of that, the antiderivative of secant x tangent x dx would just equal secant x plus c, right? And I'll, like I say, I'll give you a list. I'll put it on Moodle. There's one in your book on page 243 of all these. Okay, so we've got those to draw from. How might we rewrite this then, so it would fit one of those? Well, it clearly doesn't fit one of the top two, does it? So it's got to be one of the bottom two. So how could I write that function in terms of?
Can you take out a tangent and then 1 over cosine t?
Okay, good. Let's split up that integrand so it looks like this. So it looks like we've got a sine. Really, what we have is a sine t over cosine t times cosine t, right? So I could break it up into sine t over cosine t times 1 over cosine t, right? And then that becomes antiderivative of tangent times secant. I'll flip it around so it looks better. Secant t, tangent t, dt, right? What's the answer? Derivative of what is secant tangent? Secant, yeah. Okay.
That's gonna take some getting used to.
But you see the game we're playing. We've got to break this thing up so we can get some rule. We have to get a rule that we know. It didn't look like that at first, did it? Okay. Okay, what about that one? Actually, that one's not that bad.
Because if you secant y and then you have secant squared.
Yeah, so those are both, just by distributing, this time this is quite a bit easier. I get two rules. You know, I get a sum of two rules or a difference of two rules that are in the playbook.
So you have secant and then you have
Integral of secant y tangent y minus secant squared y dy. Whoops, sorry. Like that, right? And I could break it up literally into two separate antiderivatives, but I don't need to. I know that this one goes to which solution? Secant y. And this one goes to what solution? Yeah, minus, not tangent squared. Tangent, remember, derivative of tangent is secant squared. Plus some constant, right?
So the secant y, tangent y goes to secant.
Well, the antiderivative of that does, doesn't it?
Yeah.
Right?
Okay.
And that's just one of our rules.
Is there a rule for secant y minus
No.
No.
No. That's one we wouldn't, and you see why we don't make those, because we don't want our playbook to be a million plays long, because then it's too hard to leaf through the playbook. We just want it to be a few basic plays that we can break apart and, right, and use in different ways, okay? Oh, wow, I'm out. How about that? Okay, so, I thought there was another one in there.
No, guess not.
Guess not, no. Well, there's one I'm gonna add. Gosh,
Maybe
I
it's a
think,
sign
I must have skipped through it.
Well, I could do this as a side thing, some people are subject. Always do that. Thing to say, but I probably shouldn't use the words and this.
What about that one?
I don't know about you, but I always trip when I go backwards.
I don't think that's what I used to do.
Okay, what do you think we do with those square roots? Yeah, we're just gonna make them into rational exponents, fractional exponents, right?
Break it up.
And that the power rule applies for any exponent. Doesn't have to be an integer, right? So we could rewrite this as antiderivative of x to the 1/2 plus x to the 1/2, I guess, x to what power? Right? And now we just follow our rules. Just follow that power rule. So what is this one gonna become? So it's gonna be, n is 1/2, so our answer is gonna be x to the 3/2, right? N plus 1. 1/2 plus 1 would be 3/2. Divided by 3/2 would be the same as multiplying by, right? Okay. Plus 1/2 times x to the, yeah, negative 1/2 plus 1. I guess I do need to scoot that over, don't I?
Aren't you minusing? N minus 1?
You're adding 1, right? Because it's, remember the rule, when you anti-differentiate, you gotta make the power bigger by 1.
Okay.
So it's gonna be x to the negative 1/2 plus 1 is positive 1/2. Divided by 1/2 is the same as multiplied by, right? Make sense?
So it's
Because it's, remember, it's x to the n plus 1 divided by n plus 1. But like I say, we never, you know that if you're you always just instead, you just instinctively multiply by the reciprocal rather than divide by a fraction. Yeah. So right, so we just get 2/3 x to the 3/2 plus x to the 1/2 plus c. And you can write those as radicals if you want to. But either way, same thing.
good Lord. I don't like that fraction crap.
Okay, so a quick review, well, I mean, being as we're at the end of the period anyway, quick review of our solving differential equations. See if you remember this. What if we want to, solve the differential equation y prime equals cosine x, and we know that this goes through, we know this, we know it goes through the point, the function goes through the point 0, 4. Can we solve this differential equation?
At least, like, you change it to sign.
Yeah, so we got to remember to solve remember what a differential equation means. It just means an equation with at least one derivative in it. Well, there's our derivative, right? To solve that, we have to just undo the derivatives and write the original function.
Sin x and plus c.
Okay, good. And so, and that's good. You guys are seeing that. I mean, you know that how to set up the integral. Technically, now we know how to set this up. We would say dy dx equals cosine x. So if I write it in differential form, dy equals cosine x dx, I can just integrate both sides, and we end up with the integral of cosine x dx equals y, right, equals our answer, doesn't it, right? Y plus c.
Yeah.
Okay, so then, but you guys see that probably you can just go to that a lot quicker, right? You know that if I want to undo this, if I want to find the function whose derivative is cosine x, then you know that that's what goes in the integrand, right? So we're really just doing the antiderivative of cosine x dx, right? Okay, and what's that give us for an answer? Sine x plus c, right? So what do we call that solution?
The general.
General solution, right? That's the general solution to the differential equation. It's general because it's a family of curves. If I look at what that looks like, if I add a constant to this, if I were to graph that family of curves, it just looks like that, right? So let me see, oh, I could be really tricky with
Would there be a multiple amount of curves like that? Or, oh, never mind.
Let's see. Oh, that's tricky. I don't know that. You get, well, you see what I was trying to do, anyway. Yeah, I'm just gonna move those all up and down, it's not worth messing with, you get the idea, right?
Yeah.
So I'm just gonna have carbon copies of those shifted up and down, an infinite number of them, that's the family of curves, right? So now, how do we find the one that meets our initial condition? Because if we look back up there, at the top, we look back up there
Plug
at the
in
top,
the X.
yeah, look, we've got, we know that ours has to be the one trajectory that goes through that point, right? And so we can plug in this value of x and y, right, and get our answer. Okay, we know that our answer is y equals sine x plus c at the point 0, 4, 4 equals sine 0 plus c. What is sine 0?
1? No.
Negative.
No, that'd be power 2. Oh, okay, my bad. So that's
0, isn't it? So y coordinate at that point, so it'd be 0. So c equals 4, and our particular solution would be y equals sine x plus 4. That's going to be the trajectory that goes through the point. Right?
Yeah.
Okay. Oh, man. Oh, well. So where I'm leaving you with right now, and this is the problem that I've been waiting to get to. So what would you do if you were to do Newton's experiments, go back in time and do Newton's experiments where you were to just roll, you're going to slow down the acceleration of gravity by, say, rolling, spheres down inclined planes. But by doing that, you're able to get a fairly reliable measurement of the acceleration of gravity on the surface of the Earth. Okay, we could come to the conclusion, we could all do this. I used to do this in my physics class, it's not that hard to do. We could come to the conclusion that G is about 9.8 meters per second squared. So the question I'm putting out to you now is how can we turn that into all the equations of motion? Okay.